I would be talking about linear regression here. So if you remember from the first session that we had I had summarized the entire process of linear regression into this one simple equation, which most of you recognized was that of a straight line. Y, the outcome variable, is equal to mx plus c, where we all know that c is the constant and m is the slope of that straight line. Now, this equation could very well be rewritten with substituting m and c by y is equal to beta naught plus beta 1 x1, where c can easily be replaced by beta naught and the term mx has been replaced by beta 1 x1. So if that be the case and y is equal to beta naught plus beta 1 x1 is the understanding of linear regression in general, then the entire exercise is about interpretation and calculation and identification of beta 1. So the entire effort that we are making while doing linear regression is to find the slope of the line or to find beta 1. I hope you have been able to see the videos that were circulated. And I'm just going to highlight in the next 2 slides, in the next 5 minutes, the key points that you need to remember to understand those videos in a better fashion. So a lot of us wonder what is a model, and the statisticians often have this tendency to talk about a model as if it is something very heavy. So model is nothing but the different variables or different predictor variables that we bring in into our equation, where we had y is equal to mx plus c. We could bring in x1, x2, x3, x4. We might want to study the age. We might want to study the weight, the height. So there may be more than one factors which are there. So each time we have run a linear regression, we call it a model. So please do not get confused about anything like a big thing. It's a model. It's a simple equation that we run every time. Please understand that y is the outcome variable. In trying to do a linear regression, y is continuous. Y is also called the dependent variable. The x is known by different names: covariates, predictor variables, independent variables, or explanatory variables, and many more. If there is only one x, we call it a simple regression. If there are more than one x, we call it a multivariable regression or a multiple regression. The entire exercise, as we said, is about the interpretation of beta 1, which is the slope of the line. Now, this has been referred to by Olden in his video as rise over the run, or the rate of change of y for 1 unit change in x. Not very complicated. Just let it be at that face value. It's just the rate of change of y for every unit change in x. Now, supposing we have more than one variables, then we simply say that its rate of change in y for 1 unit change in x1 with all other x's having been held constant or having adjusted for all the other x's. So there are different terminologies which are used by statisticians more to confuse the average reader. Adjusting for is the same as conditioning on, or correcting for, or controlling for, or keeping the other x's constant. So when all the other x's do not change and there is only change in one of the variables, and we try and calculate what is the change in the outcome variable with every unit change in x1, then we call it a linear regression, or that is what we are trying to find by determining the slope or the beta 1. So there are a few key simple steps in doing a linear regression. 1, you understand your variables. 2, identify which will be a dependent variable. Number 3, Identify the independent variables that you will bring into the equation. That means which are the variables of interest that you want to study. Number four, so in this third step, while trying to identify which variables to bring in into the equation, this can be based on clinical knowledge, on your scientific knowledge, or a logical understanding of the problem. It could be based on the statistical analysis that you have done before doing the linear regression. Number four, you need to decide how you will handle each variable. We will talk about handling of variables in further sessions of this workshop, not today, later. It, it is important to remember that the software understands only 0 and 1 or numbers. So there is a specific way when you need to handle categorical variables. Number five, you regress finally. And number six, you analyze the residuals and interpret your analysis. So if you follow those six linear regression steps, then you can get the linear regression in your bag. So that is all that I have to lay the foundation of the linear regression per se. And we will have Dr. Alden Gross, who will talk to us more and introduce linear regression on this as soon as we join probably the next meeting. So in your video, Alden, you have spoken of regressing writing ability against nothing. So I had a tough time trying to intuitively understand what do you mean when you say regress against nothing. Ultimately, what does it mean when you are regressing against nothing?
So the notion of regression, and this took a long time for me to grasp and understand. The notion of regression is you can think about, can you explain this outcome variable? Can this outcome variable's variance be explained? Can it be regressed on something? And if you explain something with nothing, then you get that something back. So in this example, in this toy example, there is nothing explained by the model. The R squared is 0, the F statistic is 0, and the only coefficient you get is a beta naught coefficient. You would never report this in a paper. It's simply a toy example. Yeah, does that answer your question?
Yeah, thank you. Thank you so much. And I will now circle back to Dr. Amir here, who would demonstrate the example of doing the regression hands-on the video. And then Shailaja was about to talk on the journal article, which incidentally Alden has already read out and shown how that is done. So maybe we will skip that, Shailaja, if that's okay. And we will just have the demonstration of trying to do regression on the
Definitely, sir.
software.
I just had the article and I had a small presentation prepared. If it's okay with the cohort, then I'll just share that with everybody. And if anybody has any questions, they can just always feel free to contact me. It's just
Sure.
the presentation is just pointers to help them basically write their or report their articles better.
Right, precisely. So we'll have Amir, and then we will come back to Shailaja for a quick presentation on the
Yes, I
journal.
think.
Yes, Amir.
Thank you, Alden. Uh, so you all must be able to see the screen where this data is already open here. So we will import the file. So the first example that we have shared the in that exercises document is about the weight, height, and number of siblings. Weight, height, age, and number of siblings. So it just an example, and then let us import the data. So I'm importing the data, and this is data is in an Excel format. There are various other formats that you can use. So a box pops up where it is asking for the where is the file. So here is browse, so we click on browse, and this is the folder where I have saved. You can search other folders if you have saved it somewhere else. And this is that Excel sheet. So this Excel workbook has got two sheets. So I'll just open it. So we see worksheet one, and another is two, and I click on the second because that is where my data is there. So this I'm seeing. So the first row is having the names of the variables, but I want the first row to be the first record. So here is the checkbox, two checkboxes I am seeing. So the first one, import first row as a variable names. So I want this first row that is getting displayed here as variable names, not as data point. So I click here, and the moment I have clicked here, we see that age, height, and number of siblings, they shift to the name category, names group. So these are the names, and then I just click OK. So because all earlier some data is there, so I don't want to, so I want to override that. So I will click on yes. I want to continue and lose the unsaved data that was earlier there. So I have imported the data, and I can see my data here. Here there's an option on the top, the various options you can see: print, save, graphs, and other things. And here it is, data editor, browse. So I click here, and this is the data that has come in: age, height, and number of siblings. So what we see is that age and height and number of siblings, so age and height are the continuous variables, and number of siblings is the categorical variable. So we want to see whether the height, how the height changes with respect to age, and whether the number of siblings, do they have an effect on the height. So our height is, we are taking it as the dependent variable here, and this is dependent on what? So here it is dependent on age and the number of siblings. So let us go back the analysis part. So for analysis, we just use the statistics and the linear models, and where we are using the linear regression. The first one is the linear regression. So we have this linear regression here, and it shows the dependent variable. The three variables are here, and we can have the this independent variable. So when you will click on it, there will be nothing here. So because I had worked on this example earlier, so it was showing this. Otherwise we have to select here. So dependent variable is height, so height is selected here, and then we go on to independent variables. Now in independent variables, as we have to see, there are different types of variables. So here there's a box where there are three dots. It creates variable list. So I click here, and I want to see the continuous variable. So this is the age is the continuous variable. I So first let me make this blank. So I'm adding this, and then there is another one, is the number of siblings. This is a factor variable. So this is the number of siblings, and we have to set, whenever we have to factor variable, we have to set what is the reference value. So we can select a reference value. So the first value is a reference value, or 0 is a reference value. So I click 0 as a reference value, and I add, and I click on OK. So what we have here is the various things are here. So I click on OK, and then I get the output. So here we get the age, the coefficient is 3, and then the p value we get here, the 95% confidence interval, and then the number of siblings also we are getting, how it is, the coefficients are changing. So this is in short this particular demonstration about this thing. The another exercise, the exercise that we have given as homework is related to the data set that has been generated from the participants when you all registered, you all filled a Google form, and at the back end the data was formulated in CSV file. So that has been shared with you all, and that exercise has been given that one dependent variable has been selected, and you can select independent variables and try to see the various how the other factors are associated with that particular. So you can select based upon your own theory what predictors or what independent factors will influence the dependent variable. In the our exercise we have given the dependent variable as, I think, years of experience, I think, that we have given of the participants who are participating in this workshop.
Thank you, Alden. Thank you, Amir sir. So now moving on to journal article presentation. Just give me a second to. I hope my screen is now visible to everyone.
Yes.
Okay, so Alden has already covered most of the points that I will be talking about in this video. So I'll just make it very quick. And as always, if anything is not clear, please feel free to stop me and ask again. Just like the last time, we will have to start with what do we need to report when we are talking about reporting linear regression. So first of all, these are the basics. These we already know. You will need to describe the relationship of interest or the purpose of the analysis. So Alden has already spoken about the three major uses of linear regression. That is to quantify the association, to predict or forecast the future event, or explaining the variation in the outcome variable. So we want to describe that relationship very clearly for the readers. Then we will move on to identifying the variables. This is also a very standard procedure in any of the study protocols that we do. We start our results, we start the discussion of our results with describing all the variables in our study, the dependent and the independent variables. So the rule of thumb is for continuous variables, we will be using medians, ranges, or interquartile ranges. And for normally distributed data, we usually describe that using the means or the standard deviations, and categorical data will be presented in percentages or counts or proportions. After we've done these basic things, now we will move on to the specifics of reporting linear regression. As Alden has already pointed out, there are certain assumptions that any, for example, for that matter, any not just linear regression, but any test of hypothesis will follow. So all of those assumptions you will need to check, and it's a good thing if you report that those assumptions were checked and how these assumptions were checked. So some of them might be checked by using a graph, some of them might be using checked by using tests of hypothesis. But it's good if you report that you have checked for assumptions. It makes the reporting more robust. Then it's also good to report how many missing data were there and how you have treated that data. So since all of you are senior researchers, I'm sure everybody is aware of the process called imputation. So either you can just drop the missing data if it's not significantly contributing, if it's not making a significant difference to the analysis, or you can just impute the data, in which basically there are different methods of imputation, which will depend on the kind of variable you're dealing with. So you can either impute the data. Basically, imputing the data will mean that you're substituting the missing data with on the basis of the values that you're borrowing from the already existing data set. For example, I can take a mean of the already existing variables. That would be imputing the data in one way. Or I can take the last observed uh, reading for a participant. That would be imputating the data in another way. Any which way that you're using, you have to report that how this data was treated, how this missing data was treated. Then since linear regression, the basis of linear regression is actually that there exists a linear relationship between the predictor and the explanatory variable. So the outliers will make a lot of difference. So you will have to report that if there were any outliers or not, and if there were any outliers, how you have treated those outliers. Then finally, you will come to reporting the regression model. The regression model that you will be presenting can be either reported in the form of an equation in the text or in the form of the scatter plot, which we must have seen in Alden's video. Multiple linear regression usually is presented in the form of an equation only. After that, we all know that after performing the linear regression, after we what we will be getting is the basically the correlation coefficients. So all the p values and 95% confidence interval for all the regression coefficients, we have to report those. This has already been discussed that some of the journals prefer the 95% confidence interval over the p values, so it's better if you report both. Otherwise, your editor will ask you whatever he requires. Then it will be good and it is necessary that you explain how the explanatory variables that are finally appearing in your final model, how you are choosing those variables. So that might depend on whether on the scientific rationale behind those variables. It might also depend on your hypothesis, your particular study setting. For example, I want to change something. I want to change the time of surgery that a particular procedure is taking. So I would want to include in my final outcome, in my final model, the variables that I can actually change, and not the variables which are unchangeable. For example, if a particular procedure requires 30 minutes of a surgeon's time, then I can't change that. I have to keep that constant. But if a particular, let's say the OT preparation time or the anesthetist time can be decreased. So these kind of things, the explanatory variables that are appearing in your final model, they need to be rationalized. The rationale for choosing them need to be given. It can also depend on the basically the goodness of the model. That is, if a particular adding a particular variable to the model is adding value to the model, then you will choose that variable. If it's not, then you will drop that variable. Then you will provide a measure of goodness of fit of the model. This can be done in various ways, and this is beyond the scope of this presentation right now. So you can present R-square values, you can present the scatter plot for residuals. Your statistician will probably help you with that. And obviously, you have to name the statistical package of the program used in the analysis. It's a good practice if you do that. Now, quickly, taking up this article, I've taken this article from International Journal of Epidemiology. What they have done here is they have tried to explain the variation in the all-cause mortality rates in a 7-country study by taking the predictor variables, saturated fat, vitamin C, and smoking. So the article itself, the title itself says that the saturated fat, vitamin C, and smoking actually predicts the long-term population all-cause mortality. So basically, they took data from 7 countries. And now let's see whether they have actually reported the linear regression model nicely or not. I am sorry, I'm unable to. Yeah. So, firstly, they have to describe the relationship between the predictor and the outcome variable. And this they have stated right in the first line itself that the paper addresses the associations between the diet, smoking, and 25-year all-cause mortality. So this is the kind of relationship we are exploring. We are exploring the variation. Now, the second thing we have to do is we have to describe the statistics. We have to describe the variables that are there in our study. So they have taken all the countries from which they have derived the data. They have taken all the variables that they are considering, all the predictor variables. And as stated before, they have used mean, median, modes, and basically percentages to describe all of these variables. Now we have understood how the variables are distributed. Now we will move on to reporting the linear regression model. Before that, they have also talked about the missing data. That so basically in this study, what they did was they uh, collected data for the consumption of various food nutrients, all of these nutrients and all of the food habits. And they followed these people for 5 years and then collected data for that. So they have reported that only 56 men or 0.4 were lost to follow up. And that is why they are saying, probably that is why they did not pay much attention to this data. There was no need for imputation or anything like that. After that, for reporting their linear regression model, what they have done is they have simply to make things easier for us, they have reported the model like this, that the multivariate model is all cause mortality is equal to saturated fat plus vitamin C plus smoking, which means that the variation in all cause mortality in their model is explained by the consumption of saturated fat, consumption of vitamin C, and the practice of smoking. Now, what they did was they performed linear regression for this, and then they obtained the correlation coefficients uh, for all of these for all of these variables, and they have reported the confidence interval and the p-value for all of them that we can appreciate here. So just a quick note about the relationship between confidence interval and p-value is that when your confidence interval is crossing that cutoff limit, for example, here the confidence interval is crossing 0. We are getting a relationship that can go towards a negative side also or towards a positive side also. P-value for these kind of things will usually be non-significant. Now they have uh, described the relationship, they have reported the summary of the variables, they have told us about handling of missing data, they have reported their model, and they have reported the confidence interval and p-values for all the correlation coefficients. Now they are explaining how they are choosing the variables in the final model. So basically, they make comparison with the earlier analysis. That earlier analysis showed that the non-significant association between prevalence of smokers and 25-year population mortality for coronary heart disease became statistically significant when both the prevalence of cigarette smokers and saturated fat intake were added to the model. So the statistical significance of the model was changing, and that is how adding or deletion of the variables was being done for this model. In the present study, similar approach has been used, that the prevalence of smokers and saturated fat intake were significantly associated with all-cause mortality in the multivariate model. The model improved further, that is the R-square value of the model improved further when the vitamin C intake was added, but not when the flavonoid dietary fiber intake or alcohol were added. So that is why they have chosen to include vitamin C in the final model along with the evidence that the literature already supports. So this you get from the alcohol, and saturated fatty acids you get from the literature. Then you get vitamin C from your present study. But then you added other variables to it and you found that they were not adding much value to the model. So that is explaining the choice of the variables in the final model. And finally, they have reported the goodness of the fit model by reporting R-square values. And this is the final model that they have presented. So this is a graph that you will always get whenever you're performing linear regression, whatever kind of program you're using. And that's all.
Yeah, thank you, Shailaja, for that presentation. There are some questions which have come on the chat box, and Olden, I'll take them up one by one. So Susiana has asked, what if the outcome variable is not normally distributed? So does it matter if the outcome variable is not normally distributed, and is it that it can then be covered by the number of samples?
I saw that, and so sample size does not necessarily help you if the way that you're collecting the sample or the nature of your outcome is skewed, then you should consider a transformation of some sort. Amir asked me in a private chat, should the outcome variable be normally distributed, or should the residuals be normally distributed? At the end of the day, the residuals should be normally distributed. So really, again, I'm talking, we need to think about that multivariate normality between the combination of all the X's together in a bunch and the outcome variable. In that sense, that's partly why I said that you don't need a strictly normally distributed Y, but often the best way, in my experience, to ensure that you have a normally distributed residuals is to have a normally distributed Y variable. A complicating issue is, remember, we're using ordinal least squares regression. And in least squares regression, the goal of the regression is to minimize those residuals, those vertical bars between each point and the regression line. And the output of the regression often forces those residuals to be normal.
That from Susiana. Now there's another one which says, how should outliers be dealt with in a linear regression? So if you do have outliers, how do you?
That's a good question. You should deal with them. That's a joke. Yeah, so different people have different perspectives, and again, there's never any super correct answer. My approach with outliers is, look at your leverage versus residual plots. If those you could estimate a sensitivity analysis. Probably the best answer that most people would agree with is to estimate a sensitivity analysis in which you exclude that outlier from your regression. If that single outlier changes your beta coefficients or changes your inferences a lot, then you should consider removing that outlier, or at least looking into that data point and figuring out why it is an outlier. So in my example in class, I created an outlier in the data. I had a sample, I think in the examples, in the demonstration, I had a sample of people aged 65 to 80, I think. And I artificially changed one person's age to 40. That is an extreme outlier. So, you could run your regression with and without that outlier and see if it makes a difference. But more importantly, I think it's worth going back to the people who collected the data, or to think about how the data were collected and understand how that outlier happened. Was it a matter of weight? Is weight in kilograms for everybody, but it's being reported in pounds for that one person, in which case that's the reason for it being an outlier? So is there a mistake in the data entry, or is there something else happening? So
Yeah. So the easy answer would be to go and check the data once again, and if you find that the data point is correct, then you try and explain why that is happening.
This particular question about outliers, I think that it is important that before moving ahead and applying regression, we have a scatter plot and see how the dependent and the independent variables are correlated on a scatter plot. That visualization will also help us find the outliers and how they are affecting the whole thing. What do you think about this, Alden? Do you think it's a prerequisite to have a scatter plot before going for a linear regression, or should we just look at normality and move ahead with it?
I would say do it both ways. Look at a multivariate scatter plot of your residuals against both your outcome, your predicted value of the outcome and the x's, and look at a histogram. These things should tell you a similar story, I would imagine.
Yeah, absolutely. I think scatter plot visualization and understanding your variables is actually a prerequisite before going into any detailed, complicated statistical assessment. I'll move on to the next question. This question is, what is the difference between association and correlation in statistical analysis? How can we substitute the tests? Will method of sample size determination affect the choice, that is correlation versus association testing?
So I would say that a correlation is an example of association. the beta coefficient, beta 1 coefficient that you get out of a regression is what we would call a non-standardized correlation. So if you were to fiddle around, let's assume you have a simple example where you have a continuously distributed outcome and a continuously distributed X variable, such as in my demonstration where I was regressing writing ability on reading ability. I got a beta 1 coefficient of 0.12. Now, if I were to standardize my Y variable and to have a mean of 0 and variance of 1, and if I were to also standardize my X variable to have a mean of 0 and variance of 1, then when I conducted that, if I were to conduct that regression, then that beta coefficient would equal the correlation. So, yeah, so in that case, a correlation is or an association is a non-standardized correlation coefficient.
Yeah, in addition, what you had also spoken in your video while introducing the concept of regression, that regression allows you much more flexibility while dealing with your variables. And I don't think it really depends upon sample size or how the sampling was done, which will determine whether you will apply a regression versus a correlation, because it depends more upon the question that you are trying to answer by applying which test that will be there. We are exceeding time. I will just take this last question that is there. That is it okay just to apply present the R square in your publication, or is it better to put in the Hemshaw, Hosmer-Lemshaw goodness of fit statistics also?
It depends on the purpose of your regression. So the Hosmer-Lemshaw goodness of fit is you'll have to remind me. I think that is an index of whether the model is a good fitting model of some sort. Could you describe the Hosmer-Lemshaw test?
So I don't think we will go into the goodness of fit while trying to publish most of our articles. It's not required, and most of the journals, when presenting clinical data and presentations, do not ask for the Hosmer-Lemshaw model goodness of fit, or do not really ask for details of model fit. But it again, as you said, it depends upon why we are applying this regression. If it is just to measure the association, then it does not matter. But if we are really trying to make a predictive model and trying to explain the variability and the variation in the data, then we would need to identify which model is fitting better, and we would need to compare the models and report a goodness of fit. If reporting the goodness of fit is the purpose of the analysis, then it would make more sense.
If I can break in really quickly, if I'm going to share my screen, and I just wanted to illustrate what I was talking about, beta coefficients and correlations. So in this example, I'm regressing writing ability on reading ability. The read coefficient is 0.55. But then let's say that I standardize my writing score and I standardize my reading score. Then I regress my Z transformed writing on Z transformed reading. Instead of a 0.55 correlation coefficient, I get a 0.5967 correlation coefficient. Now here, if I correlate writing and reading, the correlation is 0.5968, which matches the 0.59677. So again, my writing and reading score, the raw scores, had means of around 50 and standard deviations of 9.47 and 10.2. But if I standardize the things, then I make them have a mean of 0 and a standard deviation or variance of 1. So that's how an association basically is a non-standardized correlation coefficient.
Yeah, thanks, Alden. I'm compelled to take this just last one more question. It's a long question, but I'll break it into parts. What is multicollinearity? Is it different from interaction? Is it same as effect modification? And what is autocorrelation? So it might require a very long answer, so we'll break with that. But yes, this is the last question we are taking definitely on this workshop.
So I would say briefly, multicollinearity is not related to interaction or effect modification. Multicollinearity happens when your two or more of your X variables, your predictors, are highly correlated with each other. And so an assumption of regression is that your independent variables, your X variables, are not correlated with each other. This is always violated, but if it's violated extensively, then what happens is that the model is not sure where to attribute variability when you have these two highly correlated X variables. You will see this when you'll notice an extremely large standard error value. Interaction and effect modification are the same thing, essentially. Interactions are asking whether the association between X and Y differs as a function of some other variable, Z, for example. And what is autocorrelation? Autocorrelation comes up when you're doing longitudinal analyses. And I think that's a little beyond what this session is designed for right now.
For an example for multicollinearity, I could say that, for example, just assume that for some reason, while collecting data, you had taken the weight of the participants without their shoes, and then you also recorded in the same Excel sheet the weight of the participants with their shoes on, and then you decided to put both these variables into your model while running the linear regression for some dependent variable, and you realize obviously both these are correlated to each other. They have huge degree of the collinearity, and they're actually dependent on each other. So there is no reason why they should both be in the same model. It's something like that, but at a very crude level, I would say. So I think we should close this session here. I have shared the exercises and assignments for you for this week on a mail. And for that, the dependent variable, you have to find and discuss in your small groups, build up your models, and then present the answers. So I think it will be interesting to identify what are the predictors for the number of publications each one of us has. And I have tried to put arbitrarily some number of publications into the Excel sheet based upon the range that you had given, which may or may not be correct. So forgive me for arbitrarily introducing some number of publications against each name, which may or may not be correct. But I have shared the exercises and the data set with the number of publications with you on email. And once again, thank you everyone for joining today. And thank you, Olden, for bearing with us despite an ungodly hour at your place. You would be running to work, and our regards and apologies to Charlotte as well.
Thank you for your patience with me. It's great talking to you all.